This is the video for the Unit 7, Lesson 2, content on polynomial functions and division. And yeah, I really wish I could be at the beach right now, but that's not a realistic idea, and I don't mean to tease you or myself, I guess. Anyway, what we'll be doing is walking through the warm-up for this lesson, which is on solving quadratic equations, and it's a review of what you should have learned both in Algebra 1 and in Algebra 2. And then I'll be going through the notes packet. And as I had done with the Lesson 1 lesson notes, it's fairly straightforward enough for you to be able to write out all these problems on notebook paper or blank paper, the back of an old worksheet or something. So you really don't need to print out all of the pages of the lessons. Just grab a blank sheet of paper and you can work off of the document that I posted on Google Classroom, or even just write down what you see in the video. Don't forget to liberally use the pause button while you work out problems, especially anything that has to do with factoring, which there will be some of, as well as to just work out some of the problems that I'm not going to necessarily talk through. Okay, here we go. If you don't have a hard copy of the warm-up number 2, then pause the video here and write down the problems. But the concept here is that you're going to solve these quadratic equations. And my hint for you to start with is just to get everything set equal to 0. And there's 3 different methods here. One of these 3 problems, the quadratic is factorable. The other 2, you won't use factoring to solve, and I'm not going to tell you which is which. Hopefully at this point you've got them copied down, so go ahead and pause the video. And in a couple minutes, I'll actually walk you through all 3 problems, but I want you to try them on your own first. Okay, so hopefully you have made a good attempt at working out these 3 problems for the warm-up. Remember that I had said that you want to get everything set equal to 0. But actually what I realized when I looked at my answer key for this first problem is that getting this set equal to 0, you can do that and you'd get the right answer, and that's not a problem. But I wouldn't start this first problem like that, because what I notice is that there's no term that just has an x. There's number terms and there's an x squared term. But if I can go ahead and isolate the x squared, then I can just take the square root of both sides, and that'll give me an answer to this problem. So I'll go ahead and add 3 to both sides. So I start with 24 is equal to 2x squared, and then divide both sides by 2. So I have 12 is equal to x squared. And remember that in this case, then, when you have x squared equals a number, you take the square root of both sides. But remember that you need to use the plus or minus in front of the square root of the number. And so then the next thing that you're going to do is notice that radical 12 can be simplified. And so, and just real quick, in case you're not sure about how to do that still, just write any multiplication problem that gives you 12 as a result, circle anything that's prime, and then break down any non-prime numbers until you get all prime factors. And then anytime you have a pair of factors, that's what comes outside. So that your radical 12 would have a 2 on the outside and the 3 inside the radical. So back over to here, plus or minus 2 radical 3 equals x. And that is the answer to number 1. In number 2, here's what I was thinking that you want to get set equal to 0. This one and number 3 both work well when you get them set equal to 0. I know that your temptation is to subtract the 6x squared so that it ends up on the left and the 0 ends up on the right. That tends to be your instinct. What happens is then that you have a negative leading coefficient, and that makes the expression more difficult to factor. And so what I would do is actually subtract the 35 and add the 11x. So I end up with a 0 over here. And then I have 6x squared plus 11x and minus 35. And I will take just a quick second to factor this for you, even though you should be able to do it without me, hint, hint. So I multiply 6 times negative 35, 6 times negative 35, and that gives me negative 210. And I want two numbers that multiply to negative 210 and add to positive 11. And those two numbers are positive 21 and negative 10. And so I'm going to replace the 11x with 21x and minus 10x. So what that then looks like in the expression is 0 equals, keep the 6x squared, and then plus 21x minus 10x, and then minus 35. The next thing I want to do is grouping. Remember that grouping is done by looking at two terms at a time and taking out any GCF that might be there. So in those first two terms, I keep the 0 equals because I want to keep all my lines consistent. This is one of the several reasons why I don't tend to favor slide and divide as a method for factoring, because in this case, each line of the algebra is equivalent to the line above it, and in slide and divide, you actually mathematically change the expression before you get to the final answer. So anyway, I'm going to keep the 0 equals there, and in my green underline, the first two terms, 6x squared plus 21x, the GCF is going to be 3x. And when I take out the 3x, that leaves 2x and then plus 7. And so that's the answer to taking a GCF out of the green part. And then remember that if the sign in the very middle of the problem is negative, then the sign on your second GCF is going to be negative. So when I look at minus 10x minus 35, I know that my GCF is going to be negative. And 10x and 35 are divisible by 5. So I'm going to do minus 5 times 2x plus 7, because negative 35 divided by negative 5 is positive 7. And what should happen then is that your stuff inside of the parentheses each time should be exactly the same, signs and everything. If it's not, you made a mistake. And here then take the two things that you took as GCFs, and those are going to become your other binomial. So 3x minus 5 times 2x plus 7. So that's factoring the expression. Hopefully you were way ahead of me on that and you fast forwarded through all of it. But then remember that when you're asked to solve, and let me just step back for a second. Notice here that the directions say solve, and solve always means find x. Or it means x equals a number, that your answer will be what does x equal. And so here, the directions didn't say factor. You have to factor in order to solve, but you're not done with the problem yet. You factored it, but now you have to tell me what x is equal to. And so what I'm going to do here is take each of these terms, or each of these binomials, And keep in mind that you have a thing times a thing that are equal to 0. And so anytime you have something times something equals 0, one of those two things or both of them have to equal 0. And so what I'm going to do then is take each thing being multiplied, 3x minus 5, and set that equal to 0, and 2x plus 7, and set that equal to 0. And then I'm going to solve both of those linear equations. And it should always be a linear equation, so it should only take 1 or 2 steps to solve. And your answers here are 5/3 and negative 7/2. In number 3, when you get this whole thing set equal to 0, you're going to subtract the 4x from both sides. And this expression here, this quadratic, is not factorable. So not factorable. So what you're going to need to do then is use the quadratic formula. And I will try really hard not to sing the song, but know that I'm singing it in my heart. So remember that when you're using the quadratic formula, you look at you have to get everything set equal to 0, and then you list the coefficients as A, B, and C. Remember that the quadratic has to be in standard form before you write out your A, B, and C. I have seen anytime I see a mistake in students using the quadratic formula, most of the time it's because they didn't write the quadratic in standard form first, which means the x squared term, then the x term, then the number term. And they tried to use a quadratic formula with their A, B, and C mixed up. Also, don't forget that because the 4 is negative, B is negative 4. It's not just the absolute values of the 3 things. So then the quadratic formula is, in my heart, I'm singing negative B plus or minus the square root of B squared minus 4AC all over 2A. Are you proud of me? I didn't sing. And then you take those 3 values and you substitute them into the formula. When you have this type of notation, negative B, that means change the sign. So if B was negative in the original function, then negative B means you're just going to make it positive. So when I substitute here, x equals positive 4 plus or minus, and I just square it. You can write 4 squared if you want to, but I know that that's 16 minus 4 times A times C, and then 2 times A. Now when you multiply 4 times 10 times 10, that gives you 400, and 16 minus 400 is negative 384, which means that your answer is going to be imaginary, but you still need to simplify it. If you do a little factor tree on the side for 384, you'll find that it comes down to a bunch of 2's, and then 1 2 and 1 3 left over. So you end up with 4 plus or minus. Remember, take out the I first, and then I think it's 6 2's, so that you have 8I radical 6 all over 20. But remember that if you can factor something out of the numerator, so here the numerator has a common factor of 4 times 1 plus or minus 2I radical 6. And 20 is 4 times 5. You can cancel those 4's. And as a result, then my final answer is going to be x equals 1 plus or minus 2I radical 6 all over 5. There's not much, if anything at all, for you to write on this first page, but I was planning on talking through it in class, and I would like for you to consider listening through what I'm going to say on this first page. It's really an overview of polynomial functions and examples of graphs and counterexamples, so that you can kind of see the category of functions that we're looking at here. And the first thing to point out is that polynomial graphs have this often, not every single time, but often have this kind of a wavy feel. I'll just randomly pick this one as an example. So you have this waviness to it in the middle that you know, up and down, kind of like waves. But it's not periodic like the sine and cosine curves or the trig function curves, because it doesn't repeat the exact same thing over and over infinitely. And the curves or the waves don't even have to be the same every time. So for example, this one is wavy in the middle, but the waves are different. And the other thing that I want you to see is that every polynomial function, in order for you to recognize the graph of a polynomial function, notice that on the left and on the right there's a steep either increase or decrease, so it goes up or down, very steep. And that means that it's not going to come back down or go back up again. And we can talk more about how you recognize that in lesson 3 when we actually go through the actually drawing graphs of these. But just notice that if you're asked to distinguish a polynomial graph from other kinds of graphs, the left and the right ends are either going to go up or down very rapidly with a steep increase or decrease on both sides. What happens, and this equation, when we're talking about polynomial equations, this equation looks a little bit crazy, but if you think about this here, all of the letters A with these subscripts are just coefficients, or they're constant terms, they're numbers. And so what you have is, in each case, a number times a variable with an exponent. And that each of those exponents, n minus 1, whatever, 2, and then here the exponent would be 1, and here the exponent, this is actually like thinking x to the 0 power. Each of these exponents is a positive whole number, so there's no exponents that are decimals or fractions or anything. And all the numbers that are the coefficients are real numbers. They can be fractions, but they can't be imaginary. The domain of every polynomial function is all real numbers. What that really means is that you can substitute. Remember that domain is your x values, and x values are the numbers that you're substituting here. And all this is saying is that there's no restriction on what x values you can substitute. It's not like the rational functions where a denominator can't equal 0. It's not like the logarithmic functions where you can't have a 0 or a negative input. It's not like a square root function where you can't have the inside of the radical be a negative number. X can be absolutely anything in a polynomial function. Now, the vocabulary that I'm going to be using throughout this lesson has to do with terms, and the terms are, let me see if I can pull a different color here. So the terms in a polynomial are the things separated by the plus and minus signs. So term, 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 term. Those are all terms in the polynomial function. A polynomial function is in standard form if you have the highest exponent first and then the exponents decrease in value and the lowest exponent last. The coefficients, like we said above, are the numbers that are multiplied by the x's. The leading term is when you've written it in standard form. So you have to write this in standard form first. Let me just add that. When written in standard form. The leading term is the first one after you've written the polynomial in standard form. And the degree, and this is something that we'll talk about a lot today, and you may not have a good recollection of this from last year, but the degree is the biggest exponent. So if I give you, and I don't have any example equations on this page that I can zoom into, but if I give you an equation and in standard form the first term is, let's say, x to the 7th, then we'll say that that's a 7th degree polynomial. And that's going to impact what you assume about the solutions and what you assume about the graph and what you assume about the end behaviors and several other aspects of the polynomial function. So the degree of a polynomial function helps you analyze the equation and the graph. Today we'll be talking about the equations, and then in the next lesson we'll be talking about the graphs. So just a little heads up on the graphs. One thing is that the graphs are smooth, which means that you don't have a sharp corner. So this is not smooth. Down here, the graph of the absolute value function is not smooth because of the sharp edge or the sharp corner there at 0, 0 or at the vertex. Whereas this polynomial function is smooth because all of the places where it changes direction are a smooth curve. And they're continuous. Continuous means that there's no breaks. We're going to spend a lot of time in Unit 9 talking about continuity. So there's no breaks in the graph. So for example, this graph on the left, if you were to draw it or trace it, you could trace the entire graph without picking up your pencil. Whereas over in this graph, there's this place where the function breaks. And although the domain of this, did you notice that the domain of both of these is all real numbers? Although the domain is still all real numbers because the place where the break in the graph is lines up with the other, so you're not losing any x values. There's this break in the graph that you would have to pick up your pencil if you were tracing the graph, stop drawing, move your pencil, and start drawing again. And so that is a place where there's a discontinuity in the graph, and we'll talk more about discontinuities when we do Unit 9. not lesson 3, unit 9. Sorry. So the other thing that I want you to see, and this is kind of under the heading of vocabulary, are the words cubic, quartic, and quintic. I won't use them a lot, but understand that they are such common vocabulary, especially cubic and quartic. When you're talking about polynomial functions, especially cubic, I may be saying blah, 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 here's these equations, this one is cubic, blah, blah, blah. That means that it's third degree. Quartic means it's fourth degree. Quintic means it's fifth degree. So cubic, quartic, and quintic refer to the degree of the equation. And I'll go ahead and apologize now if I slip into that vocabulary without knowing it. It's just because in my head, those things are exactly the same. The majority of today's lesson is going to be using synthetic division. And you should have learned the skill or the mechanics of how to do synthetic division last year in Algebra 2. But in pre-calc this year, what we're going to do then is take synthetic division and actually show a variety of ways that it's used in analyzing polynomial functions. So what I want to do real quick is talk you through the example that's already been worked out for you at the top. On the left, I give you the steps, and here on the right, I just work out an example. And what this example is doing is asking you to divide this polynomial, third degree cubic polynomial, by this polynomial, which is a binomial in the first degree. We'll call that linear. And I want to point out to you that the polynomial that you're dividing by in synthetic division will always be first degree or linear. So the next thing that you want to do is look at the polynomial that you're dividing into and make sure that you see that it's in standard form, 3, 2, 1. So I'm looking at the exponents, 3, 2, 1, 0. And then I want to make a mental note that if I'm missing is not the best word to use here, but if there's one of the terms that is skipping an exponent, so let's say, for example, there were no x squared term or something, you would need to use a 0 when you're doing the synthetic division. If you're finding yourself getting a wonky answer that's not the same as mine in a problem here or there, take a look at whether or not you maybe dropped a 0. It's the easiest mistake to make, and I might even make that mistake here. So just kind of keep in mind that that's a common error. And then the next thing that you want to do, and I think I'm going to erase all my scribbles here, so give me just a second. So the next thing that you want to do is take just the coefficients. So if you're Algebra 1 or Algebra 2 teachers taught you long division of polynomials, you will remember that it was a real hassle. And there's x's all over the place, and you're bringing things down and subtracting things and moving everything around and lining everything up, and it's kind of a hassle. What we do with synthetic division is we only work with the coefficients. So now I know that I don't need a 0 as a placeholder, and I know that my polynomial has been written in standard form, and I'm just going to write the coefficients of the polynomial exactly as they are with the signs in order, and then I'm going to draw a box with room for this other line, with room for this to write in. And then here's the tricky part. in the polynomial that I'm dividing by, you want to consider what x would equal if this were on a graph or a solution. So your thinking is x plus 2 equals 0, so x equals -2. So x equals -2, that's what you're dividing by. And the steps go something like this, and they're really quite repetitive. Bring down the first number, the leading coefficient just comes down and you don't do anything to change it. Then you multiply 5 times -2 and get -10. And then you add -6 minus 10 is -16. Rinse and repeat. So I'm going to take the -16, multiply it by the -2, and I get +32, and then I'm going to add -28 plus 32 is +4. Rinse and repeat. +4 times -2 is -8, and then I'm going to add, and when you've used your last coefficient in the top row, I always like to put a box around that number in the last spot because that's a remainder. Sometimes the remainder is going to be 0, sometimes the remainder is not going to be 0. And so if I were to ask you just to divide and give your answer as a polynomial, you give your quotient, remember the quotient is the answer to a division problem, you're going to write your answer as a polynomial. What you're going to do, and if you need to copy anything down, copy it quick because I'm going to erase all my scribbles again. So what I'm going to do then is look at, I write while I talk. The other thing that you can't see me doing is while I'm talking to you, I'm making all kinds of hand gestures. I'm talking with my hands, flying all over the place. Then I missed the clock again. With my hands flying all over the place, and then laughing at myself because I'm talking with my hands and you can't see me. Wish you could see me. So anyway, what you're going to do if I say write the quotient as a polynomial is you're going to take every number in that bottom row, the answers to the addition problems, without the one that you drew the box around. So don't include the 10 yet. And the degree of your answer is always going to be 1 less than the degree of your initial dividend. So really what you're doing is, if you ignore everything else, you're dividing 5x cubed divided by x. And so an x cubed, or a third degree polynomial, divided by an x, or a first degree polynomial, is going to give you a second degree polynomial. So it's always going to be 1 less. And then you take those 3 numbers from the bottom row of the division and you use them as your new coefficients. Start with the degree that's 1 less in the first term, and then just decrease the degree by 1 each time. In the last term, then, the last thing that you want to do then is take the remainder and write it as a fraction where the denominator of the fraction is the original divisor. And if the remainder is negative, then you're subtracting that fraction. So what we're going to do is we're going to talk through 4 different uses of synthetic division. All of what I just talked through in this example should have been familiar to you from last year. We probably only spent a day on it last year, so it's not that it's super difficult. It just was something that we didn't spend a lot of time on. So the 4 uses for synthetic division are, first of all, just straight up division, like in the previous example. We can also use something called the remainder theorem, which is used to evaluate f of x for a given value of x. I'll talk you through examples of that. Then you can use the synthetic division to see if a certain, like if I said to you x plus 2, is it a factor of this polynomial? And you can use that to answer that as a yes or no question. That's called the factor theorem. You can also use synthetic division to find all the roots of a polynomial function. If you're started off with 1 or 2 roots, you can use it to divide and find a smaller factorable polynomial that you can use then to find the rest of the roots. So let's start just with division and do a couple examples of that. So here, these first two problems, you're going to divide, and then you're going to write your quotient as a polynomial. And the first thing that I notice in this, well, remember that you're going to look to see if your dividend polynomial is in standard form. And so 3 is the biggest exponent, and the exponents are in decreasing order. And the next thing that you want to look for is, are there any quote-unquote missing terms? Well, I have a 3 and I have a 2, but I don't have an x term. And so that's going to be a coefficient of 0. And so I'm going to use a 0 as a placeholder in my division. And remember also that I am dividing by the answer to x minus 5 equals 0, so x equals positive 5. So over here, then I am going to start by taking the coefficients 1, -4, 0, and -25, and I'm just going to write them in a row. So resize this a little bit. So 1, -4, don't forget the 0, and -25. And I'm going to draw a box around that with enough room underneath those numbers to write another row of numbers. And then I'm dividing by 5 here, so I'll just put a 5 outside. And remember that you always just bring down the first number. And so I'm going to bring that down. And then 1 times 5 is 5. And then I'm going to add -4 plus 5 is positive 1. Multiply 1 times 5 and I get 5. 0 plus 5 is 5. And then I'm going to multiply 5 times 5 and I get 25. And when I add -25 plus 5, I get 0. I always stop and put a box around it so that I remember that that's not part of the polynomial part of my answer, but it's the remainder. And then I say, okay, my original polynomial was 3rd degree here, and so my answer is going to be 2nd degree, and I'm going to use these 3 numbers as the coefficients. So I'm going to start with 1x squared plus 1x to the first. Remember, I'm not writing the 1's because we don't use 1 as a coefficient. We don't write 1 as a coefficient or an exponent. That's assumed. And then plus 5, and because there's no remainder, I don't need to write anything else. X squared plus x plus 5. In example 2, I'll start the same way. I'm going to check to see if it's in standard form. 4, 3, 2, 1, 0. Yep. And I'm not quote unquote missing any terms. So then I'm just going to write the coefficients straight up. So I have 6, 11, -15, -12, and positive 7. I'm going to draw my box so that there's just enough room for another line. Remember that I'm dividing by x plus 3 equals 0, so x equals -3. Dividing by -3, bring down the 6. 6 times -3 is -18. 11 plus -18 is -7. -7 times -3 is positive 21. -15 plus 21 is like 21 minus 15. and you get positive 6. Try to do these without a calculator. I wouldn't be giving you a calculator for this on a test. 6 times negative 3 is negative 18. Negative 12 minus 18 is negative 30. Negative 30 times negative 3 is positive 90. And so my last answer there is 97, and that's the remainder. Remember that because my original polynomial is 4th degree, my quotient polynomial is going to be 3rd degree. And so when I write that out, my answer is going to be 6x to the 3rd minus 7x to the 2nd plus 6x minus 30. And then I have to deal with the remainder, and so I'm going to write that as plus, and then the fraction 97 over, and I'm going to go back up and grab the thing that I was originally dividing by. That x plus 3 is going to be my denominator. And so this big ugly thing is my quotient when I do that division problem. Now, what we called up here synthetic substitution, technically it's the remainder theorem, but pretty much most mathematicians that you might talk to, including your professors in college, would call it synthetic substitution. And synthetic substitution is when you use synthetic division and you actually get... Could you try again? For some reason, Siri thought that I was talking to Siri. Let's go deal with Siri. Hey Siri. Say hello.
Hello.
Yeah, so that's kind of what was happening there a minute ago. So let's get back to, while I paused the video to tell Siri to be quiet, I ended up getting some texts and stuff. So it's been several minutes since I paused the video, so I'm sorry if I repeat something. But having said all of that, the concept of synthetic substitution is just that you can use synthetic division, that's where the word synthetic comes in, you can use synthetic division to find, basically this question is, what's f of negative 2? Meaning that you could substitute negative 2 into this function and literally type 3 times negative 2 to the 5th power minus 8 times negative 2 to the 2nd power minus negative 2 minus 5 into your calculator and compute the answer. Or you can do synthetic division. Remember that back in the Stone Age, when we were still using a stone and chisel to compute things, the idea of using synthetic division to evaluate a function was so much easier than actually substituting into each of the x values and computing, especially when the number that you're substituting is a bigger number. So anyway, do the synthetic division the same as you always do. You don't change anything there. So I notice that I'm quote unquote missing x to the 4th and x to the 3rd. So I'm going to have 2 zeros as placeholders. And so my coefficients are 3, then 0 for x to the 4th, 0 for x to the 3rd, negative 8, negative 1. Remember that that's going to be negative 1, and then negative 5. And I'm dividing by negative 2. You divide by whatever x equals. And so I bring down the 3. 3 times negative 2 is negative 6. 0 plus negative 6, negative 6. Negative 6 times negative 2 is 12. 0 plus 12 is 12. 12 times negative 2 is negative 24. Negative 8 and negative 24 is negative 32. Just got another text. Negative 32 times negative 2 is positive 64. Negative 1 plus 64 is 63. 63 times negative 2 is going to be, wait for it, you figure it out, 63 times negative 2. You should get negative 126, and negative 5 plus negative 126 is negative 131. And notice that you're not being asked for the quotient here, you're being asked to evaluate the function. And so the way that I want you to write the answer here is f of negative 2, because that's what you were being asked here, is equal to negative 131. I'm going to do the same thing here. The function is already given to us in standard form, and there's no missing terms, so I don't need to use any zeros as placeholders. Remember that your coefficient here is going to be 1. So when I write out my coefficients, I have 1, negative 12, positive 48, and 74. And you're dividing by, this means x equals 12, right? And so bring down the 1. 1 times 12 is 12, negative 12, and 12 is 0. 0 times 12 is 0. 48 and 0 is 48. And then 48 and 12, you're just going to have to figure it out. So wait a minute, pause, multiply. Yes, it's big numbers. No, I don't feel sorry for you. And you get 576. And 74 plus 576, again, figure it out. No sympathy. Add. And you should get 650. And again, your answer is going to be written like this. F of 12 equals 650. So in the previous page, I had said that one of the things that you can use synthetic division for is to test to see if a factor is a factor, or if a binomial is actually a factor of the given polynomial. So basically, I would say here, for example, the question is given this polynomial here, this fourth degree or quartic polynomial, this is two separate questions. So I'm asking you, first of all, is x minus 1 a factor, or x equals 1, right? The question really is x equals 1 a solution, or is x minus 1 a factor of that fourth degree polynomial? And then I'm also asking you if x plus 3 is a factor of the greater polynomial, which is the same thing as asking if x equals negative 3 is a solution to that bigger polynomial. And if it's a factor, or if x equals 1 or x equals negative 3 are actually solutions to that polynomial function, when you divide, the remainder would be 0, because that would be a place where the graph goes through the x-axis, and those are the places where the y value is 0. And so make a note to yourself here that if you're asked to decide if the given binomial, if it's a factor, you test that by asking yourself if the remainder is equal to 0. If the remainder is 0, then yes, it's a factor. If the remainder is not equal to 0, then no, it's not a factor. And for those of you working on this without a copy of the packet in front of you, real quick, this is actually asking you two separate questions. It's asking you about the x minus 1, and it's asking you about the x plus 3, and it's two separate questions. You're going to do the whole process twice. And I'm going to start working over here, and so I need you real quick to write down the function here. So now you have the function written down so that you can work out the division. And so I'm going to erase my scribble. Still getting texts. They're actually from you guys, which actually makes me happy. Thank you for texting me, keeping me company. Okay, so the 4x to the fourth is a fourth degree polynomial. The terms are already in standard order, and there are no missing terms, so we don't have to use any zeros as coefficients. And I am going to write out the coefficients for 21, 25, -5, and 3. And I'm going to draw the box and bring down the 4. Oh, and I'm dividing by the first one, so x equals 1. So I'm dividing by x equals 1. Bring down the 4. 4 times 1 is 4. 21 and 4 is 25. 25 times 1 is 25. 25 and 25 is 50. 50 times 1 is 50. -5 plus 50 is 45. Keeping up with me so far? 45 times 1 is 45, and 3 and 45 are 48. 48's the remainder. Since this here is not 0, then x, and I actually want you to write it like as a sentence, or as with words, x minus 1 is not a factor. That's your answer, because remember, it's a yes or no question. Is x minus 1 a factor of this big ugly polynomial, or more mathematically, is x minus 1 a factor of f of x? In this case, no, it's not a factor, and then you used the synthetic division as your mathematical justification for saying to me your answer is no. I'm going to do that whole process again, but this time I'm going to change the number that I'm dividing by. And so I'm going to use the same coefficients. So I've got the 4, 21, 25, -5, and 3. And I'm dividing in this case by -3. So I bring down the 4. 4 times -3 is -12. 21 plus -12 is 9. 9 times -3 is -27. 25 plus -27 is -2. -2 times -3 is 6. -5 plus 6 is 1. 1 times -3 is -3. 3 plus -3 is 0. And since the remainder is equal to 0, then you can see that, yes, x plus 3 is a factor. And you can say, if you really want a complete sentence here, you could say of f of x with a period. Now, the last use of the synthetic division is a little bit more involved because it goes beyond the division, but it has to do with finding roots. And so what you want to do You have not been taught yet, well, you've not been taught, period, how to solve a polynomial of greater degree than a quadratic, meaning if the highest exponent is bigger than 2, the only way that you know how to solve those is with special factoring, like grouping if it's x to the third, or factoring out a GCF. If every single term has an x in it, then you can factor out some of the x's and reduce. In math, it's called reducing the polynomial, meaning bringing the degree down to a degree that you do know how to factor or solve. But once you get something down or reduced down to either a quadratic or linear, then you can either factor it, or at the very worst possible case scenario, use the quadratic formula to solve that, which is why we did the quadratic formula in the warm-up. And so, for example, here in this first problem, I'm telling you that you have been given this polynomial, f of x equals all this stuff, and it's a fourth degree polynomial, and it's not factorable as is. And I want you to write this polynomial as factors, and sometimes I would say to solve it, which you can do if you've written everything as factors. And the only information that I've also told you about this is that x plus 6 is a factor. And that's the important part. You know it's a factor. And based on what we did up here at the top of this page, based on all of that stuff, you know that if you get a zero remainder, that linear binomial is a factor. And here I'm telling you it is a factor. So we're going to go ahead and we're going to divide by x equals -6. Remember, you want to think about this as what would x equal. So here x equals -6. We're going to divide by x equals -6, assuming that our answer or our remainder will be 0, because it is a factor, and therefore the remainder will be 0. So I'm going to start by doing that. I'm not missing any terms, and so I'm just going to write all of the coefficients. So I've got 1 and 1 and -26 and +4 and -120, and I am going to draw my box, and I'm dividing by -6 and bring down the 1. 1 times -6 is -6. 1 plus -6 is -5. -5 times -6 is +30. -26 plus 30 is 4. 4 times -6 is -24. 4 plus -24 is -20. And -20 times -6 is +120. And the remainder is 0. And if I tell you that this thing is a factor, if you get something here that's not equal to 0, then you made a mistake and you need to redo your synthetic division. What you want to do next is you want to say, look, this thing right here is actually 1x cubed minus 5x squared plus 4x minus 20. And if that's all I've given you, if this information here is the only information I've given you, and I want you to write your answer as a product, meaning a bunch of things multiplied, and each thing is either a linear binomial or a quadratic factor. This is not quadratic, it's cubic, so I still need to factor that down. If I've not given you anything else, that means that this is factorable. So I'm going to rewrite that over here in this space. So I've got that x cubed let me fix the cubed. Hopefully you didn't see that. X cubed minus 5x squared plus 4x minus 20. If I give you something and say that it's factorable and it has 4 terms, that means that you have to use grouping to factor it. So I'm going to use grouping here, and I'm going to start by factoring x squared out, so that leaves me with x minus 5. And then I'm going to factor out a 4, and that also leaves me with x minus 5. And so this right here becomes x squared plus 4 times x minus 5. And that's not your entire answer. You want to write f of x. You want to be able to say f of x equals, and then a whole multiplication problem that if you multiplied it back out, it would give you this function to start with. And so I have to start with the one that's given, the x plus 6. And so I'm going to say, okay, f of x equals x plus 6. And then this stuff, so the x squared plus 4 and the x minus 5. And that's going to be my answer for this problem, right? F of x as a product of linear or quadratic, and this is irreducible because this can't be factored, right? That the x squared plus 4 cannot be factored, and if you're not sure, cannot be factored. If you're not sure, look at it on a graph. It doesn't touch the x-axis. So factor or graph just the x squared plus 4, and it doesn't touch the x-axis, which means there's no solutions, which means it can't be factored. If, and this is something that I should have put maybe in the directions instead of saying write it as a product of factors. If I had said, let me do this over here. If I had said solve, then you would just say, okay, so x plus 6 times x squared plus 4 times x minus 5 equals 0. And then you would say, okay, x equals negative 6 here. I'll do the two that are easy. X equals positive 5. And then this one in the middle here, think x squared plus 4 equals 0. X squared equals negative 4. X equals plus or minus 2i. And so my answers to this are negative 6, positive 5, and plus or minus 2i. And that was if I had said to you, solve this polynomial. The other thing that I wanted to point out to you is that in the very beginning of the problem, you see that the polynomial you're given is a 4th degree polynomial. And the degree of the polynomial always tells you how many solutions there are. And so here, I've got a 4th degree polynomial, and I have 1, 2, and then this is 2 separate, positive 2i and negative 2i, so there's 4 solutions here. So this has 4 solutions, and the polynomial is 4th degree. And so all of that should match up. So as you're doing these problems, kind of keep track of the degree and how many factors and how many solutions there would be. Another thing you can look at in your answer is that there are actually 4 x's being multiplied. X times x times x times x. That's 4 x's, and that would give you an x to the 4th. So take the same approach to start number 7. But number 7, I'm giving you 2 of the factors because if you divide by the 1, it's not going to be factorable. So you're going to start with this polynomial. It's a 5th degree polynomial. And you're going to divide by x plus 5 first. And then you're going to take your answer and you're going to divide the answer by x minus 2. Remember here that this is x equals negative 5 and x equals positive 2. So you're not going to divide the original polynomial by both of those things. You're only going to divide the original polynomial by the first one. So I'm going to start here, 5, 4, 3, 2, 1, 0. So I'm missing x to the 4th, and so I'm going to need to use a 0 as a placeholder. So I've got 1, 0, negative 18, 30, negative 19, and positive 30 again. And then I'm going to divide here by negative 5. Bring down the 1. 1 times negative 5 is negative 5. 0, negative 5 is negative 5. Negative 5 times negative 5 is positive 25. Negative 18 plus 25 is 7. 7 times negative 5 is negative 35. 30 minus 35 is negative 5. Negative 5 times negative 5 is positive 25. Negative 19 plus 25 is 6. 6 times negative 5 is negative 30, and the remainder is 0. That shouldn't surprise you. You knew that the remainder was going to be 0. But you needed to divide out the x plus 5 so that you could get this quotient. Now, what I'm writing in pink right now, you're not going to need to write. You can skip right over this next part, but I want you to see my thinking here. The quotient here is x to the 4th minus 5x to the 3rd plus 7x squared minus 5x plus 6. But you want to divide this thing by x equals 2. Here's the cool part. All the stuff that I just wrote in pink, all of this, you do not need to write any of that, because really all you're going to do is take the quotient row here and just copy those numbers again. So if I'm going to divide my answer by x equals 2, I'm just going to write 1, negative 5, 7, negative 5, and 6, and divide by that. And so once again, let me say that you are not going to write, oh, hang on, I wanted to erase all of that, and I clicked something wrong, and it wasn't letting me erase. Anyway, you don't care about any of that. So you're not going to write any of the stuff that I had just now written in pink, because you're literally just taking that stuff and moving it down to here, number for number. And now I'm dividing by x equals 2. So bring down the 1. 1 times 2 is 2. Negative 5 plus 2 is negative 3. Negative 3 times 2 is negative 6. 7 plus negative 6 is positive 1. 1 times 2 is 2. Negative 5 plus 2 is negative 3. Negative 3 times 2 is negative 6. Negative 6 plus 6 is 0. And again, that shouldn't surprise you, because I told you that both of them are factors, and therefore both of them are going to have 0 as a remainder. But what you really want here is this quotient. Now, we've divided twice, so it was 5th degree, now it's 4th degree, now it's 3rd degree. Each time you're dividing out a degree. And so my quotient here is x to the 3rd minus 3x squared plus 1x minus 3. And again, if I haven't given you anything more than that, then after you're all done dividing, the result is a factorable expression. And so again, I'm going to move that over here. So x to the 3rd minus 3x squared plus x minus 3. Again, it's 4 terms, and so I'm going to do grouping to factor this. So I'm going to take out the x squared. So I've got x minus 3. And then over here, the yellow, these last 2 terms, there's no number that divides into both positive 1x and negative 3. So whenever that happens, you're going to treat the GCF as 1. But please write the 1 so that you remember then that your binomial here is x squared plus 1. A lot of students forget that plus 1 if they haven't written the 1 that they're dividing out. So you've got x squared plus 1 times x minus 3. Again, this is not factorable. It would give you imaginary answers. And so if you look here, it's a 5th degree equation, and so I need 5 factors or 5 degrees worth of factors. So I've got the x plus 5, I've got the x minus 2. This is 2, so I've got 1, 2, 3, 4, and then 5. This x minus 3 is the 5th one. So I'm done. And then the directions say write the answer as a product. So product means multiplication problem. So f of x equals, and then I'm going to start with the ones that were given to me in the original problem. And then x squared plus 1, and then x minus 3. That's my answer the way that it was requested in the directions. Remember that if it had said solve, so I'm gonna say what if it had said solve, then you're gonna do this x plus 5 times x minus 2 times x squared plus 1 times x minus 3 equals 0. And your answers, you would remember that you would need then 5 solutions. And so x equals -5, positive 2. This one here is going to give you imaginary answers. It'll be plus or minus 1i, just I, and then x equals positive 3. So now I have 1, 2, 3, 4, 5 answers. And so this would be the solution set for that polynomial here, or the original x to the fifth degree polynomial. So before I get into the topic on this last page, I want to point out that it may feel to you like this is a little bit disjoint from the concepts that all tied in real tight with the synthetic division. Remember that there are still some concepts that are taught in a math class that really are offshoots of the things that we needed to be able to do before they actually used calculators in advanced mathematics. And so this is one of those topics. So I just kind of want to throw that out there in case you're looking at some of these problems thinking, what does that have to do with polynomials and division? But really, the whole reason that you want to divide polynomials, you want to learn to find factors, you want to learn to find solutions, is when you're analyzing a polynomial function, and even when you're graphing a polynomial function, it really is all about the factors and the solutions. And remember that another word for solutions is roots. And so what'll happen as you get into more and more advanced mathematics is that you'll get a polynomial function, and nobody says, like on the previous page, nobody says to you, well, x plus 6 is a factor. They'll just give you this big, huge 6th or 7th degree polynomial, and you have to figure out the factors. And it used to be that we didn't have any technology that would draw the graph for us, so we would have to draw the graphs ourselves. And it's easiest to draw a polynomial graph if you know what at least one or more than one of the solutions are. And you can analyze what numbers are possible solutions if you look at just the first and last terms of a polynomial function. And so really this topic, the rational roots theorem, that it says here at the top, the rational roots theorem, isn't even listed on the other page where I listed the uses for synthetic division, because this is technically not part of synthetic division, although it has always been taught as part of a synthetic division lesson. And so I want to get just a little bit into the rational roots theorem, knowing that the purposes for using the rational roots theorem really are starting to be outdated by the existence of superior graphing technology like Desmos or even your TI graphing calculators. And basically what this theorem says is that if you have a polynomial function, so this here would be a polynomial function. And the letters that are the coefficients are A and Q and P. So basically, if you look at the Q, the A's with the subscripts, and the P at the end, the P and the Q, the leading coefficient, and then the number that is the constant term at the end, write those as a ratio or as a fraction, with the P in the numerator and the Q in the denominator. And then you look at all the factors of P and all the factors of Q, and you write all the possible ratios that P and Q and all the factors of P and Q could make. And any rational solution or rational root of the polynomial has to be a factor of P divided by a factor of Q. What in the world is she talking about here? Okay, so example 8 says, list all the possible rational zeros, roots, solutions of this polynomial here. And so I'm looking at x cubed minus 3x squared minus 2x plus 4. And in order to use the rational roots theorem, we don't care about the minus 3x squared or the minus 2x. What we care about is the 1 here, we'll call that Q, and the positive 4. And we don't even care if it's positive. Actually, we're not even looking at signs with the rational roots theorem. So the 4 is the P. So Q is 1 and P is 4. 1 doesn't have any other factors. It's just 1. 1 times 1 is 1. That's it. No other factors. 4, the factors are 1 times 4, 2 times 2. So the factors of 4 are 1, 2, and 4. And so what I'm going to do is P in the numerator, Q in the denominator. And I'm going to write this out kind of strange at first, just so that you can kind of see all the different possibilities. And it says to start by listing all the possible rational zeros. And so I'm going to list each of them, but I'm going to list the positive and the negative possible factors. And so I'm going to start with, in the numerator, positive and negative 4, positive and negative 2, and positive and negative 1. Those are the factors that we said were the factors of P. P equals 4, 4 times 1, 2 times 2. But Q is just 1, so I'm going to list it as positive and negative 1. And then I'm literally going to take each of the possibilities. So I'm going to make every possible combination, 4 over 1, 2 over 1, 1 over 1, and then all the possible positives and negatives. And so if I make a list the possible, and this is important here, rational roots. I'm going to talk about that, what the irrational roots are in just a minute. But if I ask you to list the possible rational roots, it's 4 over 1 is just 4, so plus or minus 4. 2 over 1 is just 2, so plus or minus 2. 1 over 1 is just 1, so plus or minus 1. It would be different if your Q value was like 9 or something, because then you would have some fractions and you'd have to reduce some things. And we'll look at a problem like that in number 9 below. But you have 6 possible rational roots. But notice that this is a third degree polynomial. Therefore, there's at most 3 solutions to that polynomial. So you could have 3 rational roots, but you could have no rational roots. And so we're going to look at what the possible rational roots are here. So having said all of that, here's where it's going to seem kind of obvious to you that you don't really need the rational roots theorem, but the reason that we used it when I was doing my math in rock and chisel before they invented electricity is that what we would do is we would we would use synthetic division and literally test divide by positive 4, divide by negative 4, divide by positive 2, divide by negative 2, divide by positive 1, divide by negative 1. We would divide by every single possible rational root to see which of them actually divide evenly. And then once we get the whole polynomial reduced down to something that's factorable or all linear factors, then we have found all the rational roots. Anything else, so let's say that we decided that there's one of those numbers that's a rational root and the rest of them are not divisible or that don't give you a zero remainder, whatever's left would be how many irrational roots. And remember that irrational numbers are numbers like pi or numbers that are square roots of a not perfect square. So like the square root of 5 or something, you would get irrational roots by doing the quadratic formula on whatever quadratic factors are left, or sometimes imaginary roots. So what I'm going to do instead of using the synthetic division to test each one of those 6 roots is I'm going to look at a graph of the function. So hang on here a second while I see if I can insert a graph. Look at that. There's now a graph there. So anyway, this is the graph of that function, and I want to zoom in real quick on the graph. And I would recommend that you play with some of these graphs in Desmos so that you can kind of see the aspects of the polynomials that I'm talking about here. And what I did to make the graph look like this is I clicked on each of the x-intercepts. Remember, x-intercepts are the same as solutions or roots or zeros. And I see that only one of them is a number without a decimal. And that these two, the negative 1.2 and the 3.2 there, are probably irrational numbers. And so what I'm going to do is I'm going to say positive 1 is the only rational root, because the 1.2 and the 3.2 aren't any of these numbers. And therefore, they must be irrational. And so really here, what I'm saying, let me kind of revise that with a different color. This root is irrational. And this root is irrational. But this root is rational, and it's one of the numbers that we said was a possible rational root. And so if I ask you this question, then I would first say list all the possible rational zeros, and that would be positive and negative 4, positive and negative 2, and positive and negative 1. And then I would say determine which, if any, are actually zeros. And so I would say, okay, here, positive 1 is the only rational 0. And even if you did it the old-fashioned way with synthetic division, if you find that positive 1 is the only rational 0, because it's a third-degree polynomial, you know that there are 2 other zeros that are not rational, and therefore they must be either irrational or imaginary. So I'm going to do that whole process again, but in problem number 9, it's got a few more fraction possible roots. And so let's take a look here at the equation that I initially give you, which is this right here. So f of x equals all of this. But remember that to start with, we don't really care about anything but the p and the q. So here, q equals 3, and the only factors are 1 and 3, and p equals 2. Remember, we don't care if it's positive or negative because we're going to look at all the possible positive and negative values, and the factors of 2 are 1 and 2. P goes in the numerator. You're going to have to memorize that, p over q. P goes in the numerator, q goes in the denominator, and we're going to rewrite that with all the possible combinations of positive and negative 2, positive and negative 1 over positive and negative 3, positive and negative 1. So here I have positive and negative 2 and positive and negative 1, that's my numerator. And then positive and negative 3, positive and negative 1, that's my denominator. And I'm going to look at every combination. And the first one that should jump out at you is that you've got this 2 over 3 and you've got 1 over 3. So those can't be reduced and they're going to end up as fractions. And so my all possible rational roots are going to be plus or minus 2/3, plus or minus 1/3, plus or minus 2 over 1, which is just 2, and plus or minus 1 over 1, which is just 1. Clearly, the polynomial is a third-degree polynomial, so at most it can have 3 rational roots, but it might have none or it might have only 1 or 2. So again, I'm going to pause this and see if I can insert a picture of the graph that I've already drawn. Voila! Here we go again. I am so impressed at my mad video making skills. Okay, this is not like a snazzy cinematography video, but like I made a graph up here. And it's the graph of that function. I'm just so impressed. Anyway, once again, I have clicked on the places where the graph goes through the x-axis, and those are going to be my roots / solutions / zeros, and the x values are the numbers that we're interested in. So I've got, this is clearly rational, -2, this is clearly rational, +1, and they're on my list. -2 and +1 are on my list. But then I've got this one, and that's interesting because -0.3333 is probably going to be -1/3. And so if you really weren't sure and wanted to test it, you could do a synthetic division with -1/3 to make sure that the answer is 0. And you'll find that it is. And so for this problem, there's not going to be more than 3 x-intercepts. So there can't be any other ones other than the ones that I've circled. And therefore, because I circled 3, there can only be 3. There can't be any more than 3. So all 3 of them are rational. And so I would say something like -2, -1/3, don't write the decimal, please, and +1 are the rational roots. Now, in number 10, I'm messing up my really mad video skills by drawing random stuff on the page. I ask you to find here, and the directions for number 10 are basically the same as number 9, but in number 9, the thing that I didn't mention is that I ask you also to find all remaining zeros of x, and number 10 is the same. But because there's only 3 zeros and I found all 3 are rational, that's it. I didn't have to do any other work. But notice that in number 10, it's a 4th degree equation, and what you'll find is that there are not 4 rational roots, and so you're going to need to find another way of solving for the ones that are not rational numbers. So let's start with finding the rational roots, and I'll start by listing my p and my q. So here, q is equal to 1, and the factors of 1 are just 1, and p is equal to 6, and 6 is 1 times 6 and 2 times 3, so it's 1, 2, 3, and 6. Remember that p is your numerator, q is your denominator, and you're asked to list all possible rational roots. And so over here on the side, I'm going to say plus or minus 6, plus or minus 3, plus or minus 2, and plus or minus 1, all over plus or minus 1. And so because 1 is the denominator, all possible rational roots are just whatever the numerator is here. So plus or minus 6, plus or minus 3, plus or minus 2, plus or minus 1. So there's 8 possible numbers that could be rational roots of this function. And the next thing that I'm going to do is take a look at the graph of the function. So give me just a second to magically make that appear. See? There it is. Anyway, so let's talk a little bit about this graph because it looks just a little bit differently than the ones that were in numbers 8 and 9. So based on the degree of this function, we see that it's degree 4. There are 4 solutions. But because there are only 2, and if you graph this, you can zoom way out. There's still only these 2 places where the graph goes through the x-axis. So there's only 2 x-intercepts that you can see. And if it's degree 4, but there's only 2 x-intercepts, that means that 2 of the solutions are imaginary. You could have a double or triple root, but here there's not that, and we can talk about the shape of double and triple roots in the next lesson. That would be in a different video. But for now, we can assume that we've got 2 imaginary roots. They're not even irrational, they're imaginary. And so what I'm going to do then is, and negative 1 and positive 2 are roots that I said were possible rational roots. Again, I would be dividing, if I didn't have a way to graph this function, I would be dividing all 8 of those numbers using synthetic division. And so what I'm going to do is say, okay, I know that negative 1 and positive 2 are rational roots, but the directions say to find all roots, so I need to find the 2 that are imaginary. And so I'm going to, and I think I gave you enough space on the page. This is the place where I'm going to use the synthetic division, and I'm going to divide by negative 1 and positive 2. So I'm going to go back to my original function up here, and I'm going to do that division. And I'm going to divide twice, like we did in, if you look back at problem example 7 on the previous page, we're going to divide the same function by 2 different things that we know are for sure roots. And so we're going to do the first division and then take the answer from the first division and use that as the coefficients for the second division. So my coefficients are going to be 1x to the 4th minus 1x cubed plus 1x squared minus 3x and then minus 6. And I'm going to start by dividing by the negative 1. It doesn't matter which you start with, the negative 1 or the positive 2. You can start with either one. What you're looking for is the quotient you get at the end of the second division. If you start with the 2, all your numbers are going to be different from mine until you get to the final answer, and your final answer should be the same. So here I'm going to bring down the 1, times negative 1 is negative 1, then I add negative 2. Negative 2 times negative 1 is positive 2, 1 and 2 is 3, 3 times negative 1 is negative 3, negative 3 is negative 6, times negative 1 is positive, 6 is 0. We knew that it was going to be 0. So far tracking with me, I know I did that fast. I'm going to use these numbers. I'm not even going to write it as a quotient. That means x cubed minus 2x squared plus 3x minus 6, but I'm not even going to write all that out. I'm just going to use the 1, negative 2, 3, and negative 6 again for my next synthetic division, and now I'm going to divide by 2. Bring down the 1, 1 times 2 is 2, negative 2 and 2 is 0, 0 times 2 is 0, bring down the 3, 3 times 2 is 6. -6 and 6 is 0, and we knew that we were going to get 0. And this is the final quotient that I said would be the same if you did your division in the opposite order. We started with a 4th degree. We divided by an x, so now this is 3rd degree, and so my answer down here is going to be 2nd degree, and so I'm going to write that quotient as 1x squared, 0x, so this 0, I'm not going to write plus 0x, I'm just going to not write the x term, and then plus 3. Now, in the previous problem, when I had asked you for the product, you would have said, okay, well, this is x plus 1 times x minus 2. Those are the factors we just divided by, and then x squared plus 3. And that would be the f of x written as a product of factors. But really what we're doing is we're solving. So the directions here say find all zeros. You're actually wanting to solve this. And so that's not your answer. I know that the 1 0 is -1, another 0 is +2, and now I have to solve x squared plus 3. And so I'm going to write that x squared plus 3, set it equal to 0. Then x squared equals -3, and I hope you can see here that that automatically triggers, that the x squared equal to a negative number automatically triggers an imaginary answer, and because you're taking a square root, it'll be a positive and a negative square root of the -3. So x equals plus or minus square root of -3, but we can't write it like that. We have to say x equals plus or minus I radical 3. Oh, and I tried to draw a box around it as if I were done. But remember then that the question asks you for all the zeros, and I'm going to say something like x equals, and then -1, +2, and then plus or minus I radical 3. I don't care what order you put your answers in. And that is 4 solutions for a 4th degree polynomial. I don't know if that's too small for those of you who pause it at the end and just write this stuff down. But hopefully you can fast forward and reverse through the video to make sure that you're in the right place. Anyway, while you're looking at this, let me also say that the last 2 pages of the notes packet here are practice problems for you. So what I'm going to do in this video is have you pause the video at this point, or wait until I show you the pretty beach scene, because the next slide is a pretty beach scene. Okay, it's the same beach scene from earlier. I should have had a different beach scene, but it just makes me want to be at the beach. So if you would, in a minute, pause the video and try the problems on the next couple of pages, and then after that I will show you the answers to all of those problems just by putting the answer key in the video, like I did in the previous lesson video. So go ahead and pause it